Hello, everyone. Thank you all for coming. We're about halfway through the conference now, or just past. Is everyone having a great conference? Excellent. So we've had quite a few talks already. Some may have been quite challenging technically, but I think none have been rocket science, which is my tenuous link back to a story about 48 years ago. There was a manned mission to the moon. You probably all know the story of Apollo 13. You may have seen the film, one that came out in the 90s with Tom Hanks. Who's seen the film? Quite a few people. Quite a few haven't. I had to go back and watch it as part of my research for this talk. And it was quite an enjoyable film. If you haven't seen it, or if you haven't seen it for a while, I recommend you go and watch it. It really appeals to the engineer mindset, particularly the problem solving involved. But if you remember the Apollo mission, it had a problem on the way to the moon. They never actually made it to the moon. Don't want to give too much away, but there was a crisis along the way, problem with the oxygen tank. And in the middle of that crisis, Flight Director Gene Kranz, who's pictured here actually, this is the photo from the NASA control room, from the mission, not the film, but the actual mission. Not in real life, but in the film, he said the words, "Failure is not an option." That was actually written in for the film. We now know that expression well. In fact, Gene Kranz himself used it as the title for his autobiography. So he's ended up saying it anyway. But it's interesting we trace it back to that film. So this title is obviously a play on words on that title. Optional is not a failure. And thinking about error handling in our code, there are situations where failure literally is not an option. It's not something that we would expect given the context of the code around it. And so we need to treat that accordingly. Whereas other times, failure is actually an option. It is something that we need to expect and handle. Keeping those two things in mind will help us to decide how to handle errors in our code. But there's a bit more to it than that, as we're going to dig into. There's another play on words here, because obviously we now have the optional type, or template, in C++, and some people are using that for types of error handling. How does that fit in? We're going to look at that as well. In fact, there's lots of different ways of doing error handling in C++. Things that have accumulated over the years, there's different trade-offs, and it can be quite difficult to really make sense of what we should be doing in any given situation. What those trade-offs are we making the right choices? Is there somewhere we can get to where we don't have to make those trade-offs? It's a really interesting question. We're at a really interesting time in the study of error handling in this respect, as we're going to talk about in a little while. But I'm getting ahead of myself. Hello, I'm Phil Nash, developer advocate at JetBrains. We've got a booth out there, so you can come and see me there if you haven't done already. Come and say hello. We'll chat about our products or anything technical, anything at all, really. We're quite friendly. So do come and say hi. But back to the error handling. I want to start by going right back to fundamentals, by looking at, if this thing works, that'd be appropriate, wouldn't it? Here we go. What is an error in the first place? Like, instead of getting down to the Zen essence of the word, what do we mean when we talk about errors? Very vague sense, we could just say, well, it's what happens when something went wrong. What do we mean by that? Well, we'll dig into that at the moment, but actually this is an extract from something I saw in a tweet a few months ago now when I was first preparing this talk. It's actually part of an error message someone had in their banking app on a mobile application. I want to show you the whole thing. And I shall zoom in a bit just so you can read this, because this really is amazing that this was shown to an end user in a banking app. Now, we're technical. We can read this and we can sort of understand what's going on. It's obviously coming from something Java-oriented, but we can make sense of it. But what's an end user going to make of this? And in fact, the person that tweeted this, I don't know what their background is, whether they really understood it, but I really love their response. I'll give a moment to read that. So we do need to be careful how we communicate errors to end users. Crafting good error messages, how we propagate these things up, it's a really important topic. That's not actually going to be what we're going to talk about today. It's just to get us warmed up a bit. But there's definitely different levels that we need to propagate errors to. And the end user might be appropriate in some cases. But there's also, at the other end of the spectrum, there are things that go unnoticed for long periods of time. Error conditions or bugs that we just seem to get away with. But are we actually getting away with it? If you think about it, these are often the worst types of errors, the worst types of bugs, because they don't happen in our development environments. They happen out with the users, maybe months later, when we can't do anything about them, when we can't diagnose them, where it's really difficult to fix them. Usually because the error actually occurred much earlier, and we didn't handle it properly, and we just got left in some undefined state. They're the worst types of errors, the ones that we don't actually detect. So we need to deal with that as well. But before we get into that, I want to clarify some terms, because we talked about the error condition itself, but then we have a path through the code that we take after that, either what we call the happy path. We're all familiar with this term. But then there's another path that we take when an error occurs. What do we call that? What is the opposite of the happy path? Turns out to be an interesting question. I did a bit of research on this, and I couldn't really find much of a consensus. If you ask someone directly, what's the opposite of the happy path? They'll probably say, that's the sad path. Happy, sad, seems to make sense, but actually in practice we don't really use that term. It doesn't make sense in practice. I did find a tweet by Ron Jeffries, well known in agile circles. He asked the same question on Twitter. What's the opposite of the happy path? Got quite a lot of interesting responses, but as I say, no consensus. As well as the sad path, you got the veil of tears, the path of sorrow, lots of colourful terms. But I think we might be overthinking it a bit. The path taken after an error, we can just call it the error path. It's a bit boring, but it gets the job done. So that's the term I'm going to use, the happy path and the error path. And as I've alluded to already, there's different types of errors that can occur. In fact, lots of different types of errors. We need some way of categorizing these, organizing them, making sense of them. So I want to start with a type of error that we're going to be very familiar with. We probably will have seen this message many times, maybe even written it ourselves, and I'm sure our end users have seen it as well. This should never happen. Of course it does. That's the problem. So this is an error situation. And in a beautiful moment of irony, when I was first preparing this slide, Keynote crashed on me and gave me this stack dump. I really love the XC corpse notify there. It reminds us of that error message that we saw earlier, propagated up to the user. Who's going to make sense of that? Clearly, these things should never happen, but they do. What do we do about them? And that's just one type of error. There's three broad categories I want to talk about. That should never happen, should not usually happen. We'll look at some examples in a moment. And might happen, but we would prefer if they didn't. It turns out the bottom one's probably the most interesting one, at least for today. But just to put some examples to that, should never happen. We should never see a null dereference. We should never access something out of range, and we should never use something after free. And you could probably add some more examples of that, common things that do actually happen, but they really shouldn't. They are bugs in our code. And if we can detect them and root them out at the earliest possible opportunity, that's going to prevent those really nasty bugs that we talked about earlier. The middle category is interesting, and there's really one canonical example here. You might think of a few more, and you might make arguments for them, but this is the one I want to call out. Out of heap memory. New couldn't allocate memory. Shouldn't usually happen, but we know that it does. It's outside of our control. And we often think that we're handling it. Are we really? There's a case being made recently that actually most of our code shouldn't need to handle this, because we work on systems where this either never happens, or if it does, it's so rare that there's no real way that we can recover from it anyway. Now, there's definitely systems where we do need to take account of this. The code is written correctly to handle out-of-memory conditions. That's not most of our code. And I think it's worth making a distinction here, because most of our exception handling is due to this. And that's adding a lot of extra noise. So there's this case being made that we handle this as a special case. Maybe we should actually treat it like the top bracket. We'll talk about that a bit more in a second. When I get to the bottom examples, just some classic examples: file not found, couldn't convert something from a string, couldn't find something in a map. These are all things where, we've got the thing that we actually want to happen, but we know that something else might happen as well. We know that we need to deal with both, and it's fairly obvious. We deal with it all the time. This is where most of our error handling strategies happen. Now, we can group these up a little bit different as well. So the top box, we can call logic errors. As I say, these represent bugs in our code. There's an interesting point here. We've got an exception type called logic error. But we just said that these things should never happen. And we shouldn't be handling these errors. We can't really recover from them, as we'll talk about in a minute. So some people have said that logic error is itself a logic error. Shouldn't exist. We'll talk about what should instead in a moment. If the error doesn't come from within the code, if it doesn't represent a bug, it must come from outside the code, and therefore it must be an I/O error. Some sort of unvalidated data coming from outside. So the bottom examples, we can see how that matches up. But the middle one is a bit of a problem. And we'll get to that because the bottom examples, sometimes these things can also be logic errors. Sometimes the file really should be there. The key really should be in the map. That string really should encode an integer. We know, because of the code around it, that this must always happen. We need to be able to rely on it. So it's interesting that the type of error and the way that we deal with it is more of a property of the call site than the implementation. And yet, we usually encode our error handling strategy and approach in the implementation. Locks us in. And as we see, we're making lots of trade-offs as a result, but we then can't control. So that's something we're going to need to think about as well. We'll see how we deal with that. But let's say this middle one is a problem because, yeah, technically it's an environmental thing. It's coming from outside the code, something we don't control. It belongs in this bottom bracket, but the way we deal with it doesn't really fit in. So we could sort of lump it in with the top or sort of treat it as a special little island. It's that awkward one. Another way to name these buckets is in terms of recoverability. Because we're expecting these types of errors to occur, we need to handle them in our code. Therefore, they are, by definition, recoverable. Yeah, we didn't want them to happen. We know they can. We can take a different path. But we're still in a valid state. Whereas if the top ones happen, then by definition, we're in an undefined state. We're in the realm of undefined behavior. Anything can happen. We're likely to make the situation worse if we try to continue. This is actually a little bit of a controversial point because there are always going to be people that say, yeah, but I had this highly fault-tolerant, resilient system. It must be up at all times. Even if it's a bug, I need to carry on regardless. Those systems exist. I would argue that just carrying on as a result of catching one of these errors is not the right strategy still. If you need that sort of resilience, you really should be looking at something more like process-level isolation. Ideally, something like the Erlang model. We have lots of small cooperating processes. If one of them goes down, it can just be relaunched again, back into a valid state. You're always in a valid known state. That's the key. If you allow yourself to continue in an invalid state, you're opening yourselves up to all those undefined behavior problems that we talked about. So this top bracket, we deal with using contracts. We don't have contracts in the language just yet. We'll talk about that in a moment. The middle bracket, we can say we're currently using exceptions for this, but I would argue that we either need to terminate, or if we need to be able to handle errors, we can use error returns. And then the bottom bracket, this is where we use exceptions, or again, error returns, and we're going to weigh those up in a moment. Before we go into these in a bit more detail, I just want to give honorable mention to a fourth category, which is the errors that never actually make it to runtime because we catch them at compile time. We should do as much as we could at compile time. It's beyond the scope of this talk, but we know we have plenty of options in C++. We've got concepts, we've got spinatrix, we've got static asserts, and really just good use of the type system. We have a decent type system in C++, we should use it. Catch as many things as possible at compile time, we won't have to worry about them at runtime. If you look at other languages, you'll see that actually there's even more that C++ could do. Bounded integer ranges, dependent types, all sorts of other tricks. But let's use what we got. We can get quite far. I mentioned contracts. They are coming to C++. This proposal has already made it into C++ 20. It was agreed, I think, earlier this year. San Diego last week, there were some more refinements on it, still actively being talked about, but this one has been accepted. Coming in 20. They're going to change the way that we write code. At least they should. We need to get familiar with how these work. At the moment, the tool we have in C++ is just the humble assert. You can get quite far with that. We should make more use of it, even now. We can define contracts that are checked, at least in a debug build, give reasonable error messages when they fail. Support for contract-based programming is going to take that to a whole new level. Much finer-grained control. We can control what types of assertions there are, as well as what we call asserts. We have preconditions and postconditions. They can be in the interface. We can control what happens when they fail. It's going to be a much richer contract-based environment. If you haven't seen this already, go and see another talk on it. It's not going to be the subject for today. But I say that's coming in C++ 20. So they're the non-recoverable errors. What we really want to talk about today are the recoverable errors, how we deal with those. So there's plenty of different approaches, as we've alluded to. I'm going to go through a representative set, because what I want to do is weigh up all those trade-offs. Usually when we pick an error handling strategy, we're focusing in on one or two things that are important to us, whether it's performance or reasonability or something like that. But actually, there's quite a few different metrics we can weigh up on, and I've picked, I think it's 9 of them. Didn't count, actually. I'm going to weigh each error handling strategy up according to 8 or 9 different scores. So I'm going to keep a scorecard, starting with the overhead. I'm going to give it a score between 1 and 10, where 1 is bad and 10 is good. So it's a little bit backwards in this case. A high number means low overhead. Sorry about that. I meant to fix that up. In fact, when we talk about the overhead of our error handling, we also need to distinguish between the overhead on the happy path and the overhead on the error path. And for different people, different parts of that are going to be more important than others, or at different times. So we need to be able to distinguish the two. We're also going to look at the safety of our error handling approach. How easy is it to use correctly? How hard to misuse? That's important. What noise, what boilerplate does it introduce to our code? How much does it intermix with the happy path? Again, this one is a bit backwards. A high score means low noise. And separation of paths is very closely related to noise, but if you have a very clear separation between the happy path and the error path, makes things a lot clearer, reduces the noise, but it's a separate thing in its own right, so I'm going to keep a separate score of that. Reasonability. It's a little bit harder to define in the abstract. It should become clear as we go through, but this is the ability to reason about the error handling, knowing what things may or may not propagate what errors and how we should deal with them. It's more obvious in some cases than others. Composability. This is actually 2 things. This is the composability of functions and objects with themselves. How much does error handling get in the way of that? But also the composability of the error handling itself. There may be 2 aspects to it. I'm just going to give a single score to them. And finally, the message. This just means what extra information about the error can we convey other than just whether an error occurred. So they're the metrics we're going to look at. So I'm now going to go through a number of different error code-based strategies, see what the scores look like. So for each of these, I'm going to look at this particular example, creating a directory in the file system. It's a good example because it's very clearly something to do with I/O, something outside of the code. If it fails, it's outside of our control usually. A classic C-based error handling strategy. We're using C++ types. So we've got a sys string for the directory name, returns a Boolean. Usage is unsurprising. We just call it with a string, put it in an if statement. The if part is the happy path. The else is the error path. So nothing surprising about that. So it's easy to think about. First thing I want to note is this Boolean return. I'm going to argue that this constitutes what we call marked propagation. I'm going to use this term a lot. This means that we can see, by looking at the function, that an error may be an error may come out of it and where it's going to come from. Now, we do this by convention in this case. There's nothing that actually says Boolean means an error. But if it's not a predicate, then a function that returns a bool, we usually infer that means it conveys the error status. Strong enough convention that I'm happy to call this marked propagation. Let's have a look at the scores then. So the overhead's pretty good, both on the happy path and the error path. In fact, about as good as it gets. We're just paying the cost of the Boolean return and an if. Both of those can be really aggressively optimized these days, especially if we're allowed to use speculative branch prediction. The safety, though, well, actually, before we get to that, the reasonability is also pretty good. As I say, we can see that it's got a Boolean return. We can infer how we're going to have to deal with that. But we can reason about it reasonably well. Apart from that, though, the scores are pretty low. Safety is down because it's very easy to ignore that error return, and there'll be no immediate consequences to doing that. It's going to lead to undefined behavior later. That's pretty bad. It's pretty noisy because we're just using normal control flow. Error and happy path are mixed together. It's not quite so obvious in this simple example, but the more nesting you get, the more complex that gets. There's no separation of paths, as we said. So that's the lowest possible score. Composability suffers because we're using the the return channel for the errors. So we can't use that to return values that we're going to compose with other functions. That gets in the way. And the message score is low because we're only saying that an error occurred, not what the error was. So a bit of a mixed bag. See what we can do to improve it. You're probably thinking we can fix the problem with ignoring the bool by using no discard. You'd be right. That improves our safety score because now we can't ignore the Boolean return. Or at least if we do, the compiler should shout at us. It's not required to do so, but it should do. But that's about the only difference that makes. So what else can we do? We can address the message score by returning something else, something a bit richer. I've used an int here. That could stand in for an enum or something else that's a bit more expressive. But that improves the message score. If it's an int, that tells us what the error might be, but maybe not any contextual information. So there's still a bit more room for improvement. And the safety goes down now, because now it's even harder to use. We've got the separate int result in there. We've got extra steps we need to take, so it takes a little bit of a hit. So again, small trade-offs here. But what we can do is now we've got finer grained control over what we treat as an error, the call site. So if the directory already exists, that may actually be conveyed through an error code. And now we can capture that on the happy path. We couldn't do that before, so that's a win. Next thing we could do is pass the error code in as an out parameter, usually by reference, maybe by pointer. Mostly works the same way, but it's actually even harder to use, so I'd say safety is down. Reasonability, again, it's harder to reason about now because it's not as obvious that this means that it's an error code. But composability improves because now we're not blocking that return channel. We can use that for composing functions together. So trade-offs again. We might address some of that by mixing things together. Here we've got an out parameter to convey what the error was, but a Boolean return to tell us that something went wrong. So we get some of our safety back. Now we can use no discard again. Reasonability is improved, but now the composability goes. So it seems like we can't win there. So maybe we'll try a different approach. Maybe we put the error code in a global variable. These days, modern architectures, that's probably going to be a thread local variable. Well, notice I've referred to this as unmarked. Now there's nothing in the signature of the function that indicates that an error may come out of it. And that's a problem, because that really impacts the safety. I've given it the lowest possible score. It also affects the overhead, because if it's going to be in thread local storage, there's a cost of accessing that, and we're going to need to check that on every function call. That's bad. Not as noisy, though, because we've cleaned the function signature up a bit, at least. But it's harder to reason about, again, because it's unmarked propagation. And composability is fine, I suppose. Again, we can mix things together. We can mix a Boolean return with the global error code. We see this a lot, actually. And that gives us better safety. Again, we've got no discard again. Better reasonability, but composability suffers. You can see that we're trying all these different things. They've all got different trade-offs. Nothing's perfect. That's the point I want to get across here. Maybe you don't agree with the specific numbers. This is all finger-in-the-air stuff. It's not particularly scientific. Don't get too distracted by that. But hopefully you agree with the general assessment that you push in one place, it pops up somewhere else. So that's sort of where we were some years ago when we decided there must be a better way, must be a better approach that we can try. And that's how we ended up with exceptions. Exceptions will solve everything, yeah? Exceptions are the primary method of error handling in C++ today. Let's see how they stack up. So straight off, we can say, well, we've got unmarked propagation. You might argue that if it doesn't say no except, then that means it must be able to throw. But of course, we have a long history of not having no except, which doesn't mean that it doesn't throw. There's lots of well-designed functions that are not designed to throw, that are not no except. So we can't really rely on that. Let's keep it unmarked. Not going to talk too much about the usage because we're familiar with it, of course. Let's go straight to the scores. The overhead on the happy path is pretty good, almost perfect. That's what we're optimizing for here, especially if we're using table-based error handling, which most platforms are these days. It's the overhead on the error path that really suffers. Given it the lowest possible score here, that may even be understating it. It really is abysmal. And we'll tell ourselves this is okay because we only use exceptions in exceptional circumstances. So it's fine to optimize for the happy path, but if it's the primary mechanism for error handling in C++, then really we should be using it for more things. And this is why we get a bit of mixed messages. Should be using exceptions or error codes or something else. Still a problem. Safety is pretty good. You're pretty much forced to deal with the exception. If you don't, you're going to find out sooner or later, maybe at runtime, but you will find out. So I'd give it a reasonable score. Noise is pretty good, because now we've got the separation of the happy path from the error path. So our happy path looks a lot cleaner. We don't even need a try-catch in every function that an exception may propagate through. So that's good as well. So separate paths gets a perfect score. Reasonability is okay, but because we've got unmarked propagation, that takes a hit. Maybe 5 is even overstating it. Composability, though, is pretty good, because now nothing blocking the error channel. Functions can compose as much as they want, and the error handling itself composes as well. As I say, we can propagate exceptions across functions. We can catch them wherever we feel appropriate, and we can convert errors of one type to another. That's fine. And of course, message gets a perfect score, because we can put anything we like in there. So, yeah, it looks pretty good, but we're still making trade-offs. There's still room for improvement, particularly on the overhead on the error path. We'll look at that a bit more in a moment. Maybe look at some numbers. Just want to mention this briefly. We had that situation where creating a directory might already exist. Is that an error? Naively, we might say we'd have to deal with it like this, and we've got this really ugly extra happy path in a catch block. We don't want that. We'd probably rewrite create.dir or Wrapup or something like that, so we don't have to handle that. But what it's worth mentioning, we have to think about these things. Mention some numbers. We don't really have universally reliable figures. A lot of people are coming up with different benchmarks. I stole these ones from Noel Douglas, who did a talk here last year on proposed still expected, which we'll talk a bit more about in a moment. These are his benchmarks. He freely admits they're not completely representative, but they do give us an indication to how bad things are. So this is the cost of returning an error up 10 stack frames on an x86 architecture, so there's a few assumptions built in. The yellow bars are by exception. The other bars are various types of error returns. The differences between them are not important for this. The y-axis is exponential. And that means that the cost of exceptions, this is on the error path, the cost of exceptions is 2 to 3 orders of magnitude slower than the error returns. Let that sink in for a moment. That's pretty serious. On all these different compilers, all about the same. It was Niall's finding. That's pretty damning. In fact, in the 2018 C++ Foundation Developer Survey, 52% of C++ developers reported that exceptions were banned in all or part of their project code. i.e., as it goes on, most are not allowed to freely use C++'s primary recommended error handling model that's required to use the C++ standard language and library. That's a really serious conclusion, made by Herb Satter in a paper that we're going to talk about a bit more later. More than half of all C++ developers can't use the primary error handling mechanism in C++. There's definitely a case to be made for going beyond exceptions. Where does that leave us? Let's have a look at something else. You may have heard people talking about ADT-based error handling. What does that mean? ADT stands for algebraic data types. If you read my abstract in the program, there is an error there, ironically. For some reason, I wrote arithmetic data types. I only spotted that yesterday. I meant algebraic data types. They're called that because we've got two categories. We've got product types, which is anything which has an aggregate of members, classes, structs, tuples. And then we've got sum types. It's actually the sum types we're talking about. Really, it should be sum type-based error handling. And here we have optionals, variants, stood expected, anything which represents a choice of types, as opposed to an aggregation of them. So let's have a look at how they might help. This is an example of a date class. I originally had an example earlier. I had to pull it out for time, so I'm picking up from there, where I was sort of trying to build a bit of a contract. But instead of having this contract-based version, we want to return a stood optional instead. So we've got a helper function here, make, a static member of this date class, which will validate our inputs, and if it doesn't pass, we just return an empty optional. And if it does, we return our valid date. Nothing particularly clever going on there. It's just how we use standard optional. Notice now this makes it marked propagation. That's how we would use it. So because stood optional has an explicit Boolean operator overload, we can use it in an if statement. So we can detect the happy path. We dereference the optional with the star operator to get the value out. Otherwise, of course, we've got the error path. So it's similar to error codes, but we've actually got the value mixed in there as well. So let's see how that stacks up. I should say also, if you do want to use this approach, I do recommend, if you want to expose undefined behavior, just mark that out with a really ugly function name. I'll skip over that for now. The important bit is the scores. So overhead on the happy path and the error path is reasonably good. Maybe not as good as the error codes. Maybe they're about the same. That depends on some factors. So it could be an 8 or a 9, but they're definitely up there. Safety is now much better because now you're pretty much confronted with the optional. It's in the signature. You have to dereference it at least. You can dereference it without checking it, but that's on you. So it's not a perfect safety score, but it's pretty good. It is quite noisy, though. We're still mixing error handling in with normal control flow. Again, that's not going to nest very well. We don't have separation of paths. Reasonability, though, is very good. We can see from the signature what's happening. We can see from the usage code what's happening. No problem there. Composability is OK. It's not perfect, but possibly using some helper functions, we can get these things to compose quite nicely. We'll see that a bit later. With optional, though, we're really in the same camp as the Boolean return. We're only able to tell whether an error occurred but not what it was, so message score is low. So we can reach for one of the other sum types to improve our message score. Let's try std variant, because now, rather than just empty or a type, we can have a choice of types. So same example, but now we're returning either a date or I put std string here. You probably want something more custom to indicate that it's an error, but it works just for the sake of this slide. So now we can actually indicate what type of error it was. We've got a few different returns in there. In the usage, well, one way to do it is we use std holds alternative to see what type it's actually holding. And then we have to get that type out of the variant using std get, the date or the string, which I think is pretty ugly, unfortunately. Does the job, improves our message score. I'll put safety down, because now it's getting harder to use. Noise is about as bad as it gets. That is really noisy code. And everything else is about the same. So I'm not sure that's an improvement much. What we really want is something a bit more customized to the task at hand, just to clean this up a bit. And that's what the proposed std expected does. Works in a similar way. I should say, first of all, we can clean this up a little bit if we use std get if, which converts it to an optional. So now we can dereference it the same way as before. And in the case of an error, we still use std get. So it's a bit of an improvement. I wouldn't say too much, just improves the noise a bit. What I meant to say was std expected. This is still going through the standardization process. As far as I know, it's still on track for C++20, but it's not been merged in yet. So hopefully we're going to get it for C++20. If we do, this is what it's going to look like. Very similar to std variant. Here I've got a date and a string again. Again, you can use a different error type. The usage is now much cleaner. This is much more like optional, except that in the error case, we just use .error to get our error type out. That's exactly what we want. It expresses our meaning much more closely. So safety is up. It's much easier to use. Noise is better. We're still mixing control flow in. Everything else is about the same. We still seem to be in a situation where we're just pushing around the trade-offs. I think we're getting some sort of improvement, but we're not there yet. So for all this talk of ADT-based error handling, where are the results? There's a bit more that we can push this. To talk about this a bit more, I want to introduce slightly more complex examples. We've just been looking at single functions so far, and we talked about composability. So I want to introduce two functions that we want to compose together. I've got toInt that's going to convert a string to an integer, and then divide that's just going to divide two integers. Both have error handling in. In the divide case, we're going to handle division by 0. We're going to use std expected. How does this look in our usage code? Now you can see what I mean about the noise and the composability issues. Just to make this absolutely clear, the bits in yellow are the happy path. Everything else is boilerplate, introduced purely by the need to handle errors. This is not what we want. It's dominated by the error handling. And this is the good stuff. But we can do some things here. One approach has been proposed by Simon Brand. He wrote a blog post about this last year, functional exceptionalist error handling with optional and expected. It's a good read. It's got some good examples in there. He's actually since proposed this for standardization. And I was in San Diego last week. And again, I think this is on track for C++20. So this is going to extend the actual interface on optional and expected with some new methods. While we're waiting for that, we can approximate the same thing by using a helper function. So this is my take. There's a bit of boilerplate here. This is just a helper function. We don't technically need the stuff at the top. That's just so that we can use one function here. We could do it with two functions, and it'd be a bit simpler. There's actually not that much going on. Just going to walk through it. So this is the function that takes a std expected. obviously heavily generic, and a lambda. In the body, we just do an if on the expected, see whether it's got a value or not. And if so, we pass it on dereferenced to the lambda. The reason for all the stuff on the top is so that whatever the lambda returns, we make sure it's always a stood expected. So if it returns a stood expected, we just pass it on. If it returns something else, we wrap it in a stood expected and pass that on. So we always return a stood expected. That's why it's a bit more complex. In the error case, we just take the error out of the expected and wrap it in a new expected, because they may be of different types. That's the only reason we do that. But now we've actually abstracted the bit that was creating all the noise. To see what I mean by that, let's have a look at how we use that. So here's the same example again, now using that helper function, sorry. So we can see our toInt in the middle, we pass that to with. The result comes into the lambda. Already dereferenced for us, we don't have to do that, so that's a bit safer. Then the result of that goes back into with again, and comes out, passed on to the second lambda. We've removed all the ifs, we've removed all the control flow, but we've created a monster at the same time. I think this is even worse. Now it's even less obvious what the control flow is, even though we've actually removed the control flow keywords. So we're still not quite there, but we only have to make one small change to this to make it a little nicer. And the reason is C++ doesn't do functional composition very well. If we had a decent functional programming language, this would be easier. We can approximate it by changing our helper function to be an infix operator. Actually, we should look at the scores first. Sorry, I jumped ahead. Safety is way up, but the noise is way down for the reasons we just discussed. But other than that, scores are getting pretty good. We'll come back to that in a second. Here's the operator. It needs to be an infix operator. I've used the pipe operator. That seems to be the common one used. There is a proposal going through at the moment, probably not on track for 20, for what we call the workflow operator, and that's pipe greater than. Familiar from other languages you may have seen. It's playing the same role, but it's dedicated to that task. Solves some problems with precedence here. But let's have a look at how that changes things. Just by making that one change, here's what the code now looks like. See the value going in at the top, passes from line to line, and pops out the bottom. Much more natural, much more readable. And again, the highlighted stuff is the happy path. There's still a bit of boilerplate there, but now it's much more regular, much more easy to reason about. So I think this is a big improvement. Got a little bit of room to go, but we're definitely getting there. So check how that affects the scores. So again, that lowers the noise. It's still not perfect, but composability is way up, because now the functions are just dealing with normal function things, and the error handling is dealing with error handling things. They're kept separate. That's what we wanted. In fact, we are using composition to make this all work. So that's good. But we've still got that noise. Still got a bit of noise there. Can we do better still? I mean, this is about as good as we can get in the language today. To go further than this, we're going to need to change our language a bit. So what do other languages do? This problem's been solved before. This is a functional approach to error handling. What do functional programming languages do? Let's go to the top. Have a look at Haskell. Haskell deals with monads all the time, and that's what this is, an error handling monad. So in Haskell, they have syntactic sugar for handling monads. It's called the do keyword. And as I said, it's syntactic sugar for use with monadic expressions. And here's this example. So obviously, we already had the do keyword, means something else. Here, it just means everything in this block. Rewrite it as if it was like at the bottom. So the greater than and the greater than equals is playing the same role that our pipe operator was. So it's rewriting what we just saw into this much more imperative-looking thing. But the semicolons are also different to what we're used to. You may have heard the term programmable semicolons. That's what this means. Where you see a semicolon here, that's where it's going to bind each lambda together when it rewrites it. That's what that means. So we get this transformation from this sort of nice linear style with no other extra code to the thing at the bottom. How would that look if we did something like that in C++? We're going to take this a step at a time because there's a few things we can't quite represent the same way. So here's the example we were looking at. If we use the do keyword, so let's set aside for a moment that do means something else. This is do from Haskell now. That means rewrite this expression to what we had before. So the same way, the semicolons, the Haskell semicolons, that means resequence this and bind the lambdas together. Okay. Good start, but there's some problems. We can't use do, we can't use semicolons. So instead of the semicolons, what if we use a keyword? I'm going to go with try, because that's familiar. That means something else. In terms of error handling, gives us a very clear indication of what's going on. It's playing the same role as the Haskell semicolon. That means that this represents a bind of two lambdas. Now our semicolons are the C++ semicolons. So that's better. Okay. Now I didn't like all the last bit of the happy path being at the bottom. If we move that into the do block as well, we can also move the error path into a dedicated lambda at the end that we pass to a method on our error object. Call it catch, because why not? And now it looks a little bit more familiar. But really, it's just transforming back to what we had before. Now, do is still a problem. Let's change that. Well, because we use catch, let's just reuse the try keyword. This means something slightly different to try today. This would work if we only use this in a context where our current exception handling mechanism is not currently used, is not going to be used. We'll come back to that in a moment, so just trust me for a moment. So we've got try, we've got catch, we've got the try keyword in there. How does the call E code look? Here was our example, divide, currently returning stood expected. Since we're getting the compiler to rewrite stuff for us, let's say that instead of stood expected of double and string, we're going to say froze to mean the same thing. Again, the compiler can rewrite it to what we had before. Instead of returning stood make unexpected, we can say throw. Now, remember I said we need to do this in a context where the compiler knows not to use the try keyword, the try statement, the same way as we currently do. That applies to throw here as well. And the thing that indicates that is that this function is marked froze. In a function marked froze, when you see throw, it actually means translate that to return, wrap in the object with a stood expected or something like that. That's how this works. And the same with the bottom. Since we're getting the compiler to rewrite stuff for us, let's sort out the catch as well. Yeah, it means the same thing, but now it's much cleaner. We've got try, catch, looks familiar, but it's doing something very different. We just walked through how we can trace this directly back to that ADT-based error handling. Basically means the same thing. It's a really important difference because we saw how the trade-offs were different. In particular, other differences to exceptions that we have now, which solve some other problems. This is all marked propagation. We've got the throws keyword there. That always means that this can throw, and if it's not there, it can't. We've got the try keyword before a throwing expression. We can reason about lines of code that may propagate errors that would otherwise be invisible. That's not strictly required by the compiler. It could do this rewrite without it. That's for the programmer, to be able to reason about the code. We can consider an optional part of this. How does this score? I think it's pretty good. The overhead on the happy path and the error path is about as good as it gets. It's about the same as ADT-based or error returns. You could argue it's even better because if we bake this into the compiler actually has more scope to optimize it even more. We could even put this up to a 10. You might quibble with that, but I think it's possible. Safety is perfect because we've got all the reasonability of exceptions that we have now, plus the marked propagation. It's about as good as it gets. You've got the lowest possible noise. You might not like the try keyword in there. Some people don't. I think it's a price worth paying. I'll knock a point off for that, but that's about it. We've obviously got the separation of paths, perfect reasonability, for all the same reasons as exceptions, plus the marked propagation. Composability is fine, and the same story with the ability to convey extra information in the message. That's almost perfect tense. We're not too far away from this. And this isn't just pie in the sky thinking. There's a real proposal for this. Some of you may have already seen it now. This is zero overhead deterministic exceptions, throwing values. I skipped over the values part, but that's an important part of it. You can actually have arbitrary payloads, but that's not required. It's got Herb Sutter's name on it. This is one to take seriously. There's a lot of other people involved. Noel Douglas, that we mentioned before, in particular. There's also a couple of supporting proposals, which I'm not going to have time to talk about now, but I'm going to give you a link in a minute to a page of references for this talk. It's got about 6 standards papers and about 27 other references, loads of material if you're there. But I'm going to finish this talk for now. There's the link, level-of-indirection.com/refs/CVP-optional. So I'll leave that up there. You've probably got some questions. I don't know if we have time to take questions. Thank you. Do we have microphone for questions?
Yeah. Now, there seems to be 2 differences between what you're suggesting or what Herb is also suggesting, and another implementation of error handling from a different language. And that's checked exceptions in Java.
Right.
It seems like your advantage is you don't have unchecked exceptions, so that helps the compiler and also helps the programmer, maybe. The other is that try keyword on throwing exceptions, which I like.
Okay.
But checked exceptions in Java are hated. Everyone thinks they were a mistake. Why is this not a mistake?
Yep. Remember, we did have checked exceptions in C++ as well. Technically, we still do, but they're deprecated. In fact, we're repurposing the keyword for this. The reason this is different is for the very reason that we didn't like checked exceptions, is because we needed to actually specify the type of the exception everywhere. And that made things very brittle, and particularly made it viral as well. You had to propagate all these types all the way up the hierarchy. And so what we ended up doing, or in the Java world at least, is making everything just throws exception, just a base class. This is sort of the equivalent of that. This is only telling you whether it throws, just not what it throws. That's still left as a runtime thing. And really, that's the best approach. The actual language that this is much closer to is Swift. It's almost identical. And in fact, Swift is one of the inspirations for this. And Swift was developed by people that come from a strong C++ background, that they've seen all of this. They come up with their error handling model as a result of taking all that into account. And they decided that, whether it threw an exception or not was the important thing. But we can get away with most of the problems if A, we don't mention the type, and B, this is all statically checked. So the compiler will always tell you if you've missed out the keyword. Again, the try keyword on the expression is an optional part of this proposal. Not everyone likes it, but I'm definitely in the camp that thinks that's necessary. In Swift, they do have that. They also have some extra features around it as well. But yeah, Swift is the model to look at. They've been using this quite successfully.
Okay,
thank you.
Hi. If I understood you correctly, the change introduced here would be somehow to push the state expected or outcome or something like that, to push it into the compiler, into the language.
Yes.
So that in a way you would change the return type of every function that's marked as throws.
Yes, that's correct.
I have 2 questions about this. The first is from maybe a debugging point perspective, you hide an underlying abstraction, which C++ people usually don't like. In a sense, what would you see in a debugger as the type of the auto of the return value? Would you see a pair of result, or not a pair, a union of error result as still expected is implemented, or something else? And the other question is, I don't see how that would scale the way current classical exceptions scale. For example, you have a function B which calls function C that can throw, and there is no try-catch in C, but this still works because A that calls B can have a try-catch. In this proposal, it looks as if the caller always has to be aware of the fact that what it calls can throw. How does it work if it's not aware, in some sense? I don't know if my question is clear.
I think so. I'll try and answer that in reverse because I'm already forgetting the first question. We'll come back to that. But for the second question, you don't have to put the try-catch in each intermediate function, but you will have to put the throws keyword and the try expression in there. So in that sense, it is a bit viral, but it's only those two keywords you have to put in. And I see that as a good thing, because now I can see exactly what points in the code exceptions may propagate through, and I don't have to make assumptions about the rest of the code. Or rather, I can make assumptions about the rest of the code. Again, this is exactly the model used in Swift. And from what I can see, that seems to be working out quite well. There were some initial grumbles, but people have got used to it pretty fast. So I think it's worth the trade-off. As I say, the try expression is an optional part of the proposal. If we didn't have that, then it's only the throws keyword that we need to put on there. Even that you can miss off, because one thing I didn't go into is how this interoperates with our current dynamic exceptions. If you put the throws keyword on the function, it means that this function uses the new static exceptions. If you don't, then any static exception that passes through gets converted to a dynamic exception, and vice versa. If a dynamic exception passes through a throws function, it gets converted to a static exception. So it's not something you want to happen too much, but it does mean that they do interoperate. So if you don't mark an intermediate function as throws, a static exception can still propagate through in the same way that a current dynamic exception could, because it gets converted along the way. So that was your second question.
Yes.
Remind me what the first one was again. Oh, the debugging. How does it look in the debugger? I think that's still a bit of an open question. I'm not sure that's addressed by the proposal. There's no implementation of this yet, other than library-level implementations like boost outcome, as you alluded to. I would imagine that because this will actually become a first-class language feature, although conceptually we can map it back to the ADT-based exceptions, it's actually a separate mechanism under the hood. And so it would just appear as a function marked throws. But we're not there yet, so maybe we'll have a better picture of that later. There is another open question that usually gets raised, so just to preempt that. Can you treat a throwing expression as if it returns as sort of expected or something like it at the point of call? And as the proposal is currently written, you can't. It's always treated as a propagating exception. But there are many people that would like to be able to handle that locally, including myself. So that there may be an extra proposal to build that in which case choosing to treat it as if it returns something rather than through something may yet be an option, but there may be complications to that as well. So I would imagine it would be just not visible as a separate type.
Great, I'm on your side there. And one quick remark, sorry. When you mention the marks, according to which you measured all the approaches, one was missing in my opinion, and that's the overhead of code size or bloat. And the current exception mechanism is exceptionally bad in this regard.
Right. Yeah, there will still be an impact on code size, because you can imagine that instrumentation of passing values down. They would be there anyway if you were using error returns or ADT-based returns, so it's a case of what you compare it against. There's an overhead compared to no error handling, probably no overhead, maybe even negative overhead compared to error returns. So I think that stacks up quite well. Next question.
Hi. I would like to say I'm in favor of this proposal because I think it's a great idea and it helps with composability of functions. But I think it's doomed if exceptions stay in the standards. And my question will focus on new, because is there some kind of proposal to make sure that new uses this feature if it is merged? Because otherwise new will still throw exceptions and then you get nothing because people will have to deal with exceptions.
Yeah, so I called out new earlier on, but sort of left it dangling a bit. In this proposal, it's discussed at length along the lines that I mentioned earlier, and an optional part of the proposal is to change default new handler to not throw an exception, but to terminate. Getting some pushback, but there's also a lot of support for it, for the reasons discussed. It does mean that if you want the current behavior, you can still install your own new handler that throws, but it does mean that people will be able to compile with no exceptions and actually have legal standard behavior and then use exception propagation using the new mechanism. That's where we want to aim for. We want to bring people back into the fold that are currently not using standard C++ because they're not using exceptions. And new is an integral part of that, because that's the main place that the standard will throw at the moment is things that may allocate. So that's what the proposal says. I encourage you to read the proposal if you're interested, as that will go into it in more depth. Okay, so I think that's what we've got time for. You can catch me afterwards for more questions. So thank you.